third finished, and the actual the present version you find on her homepage. So this is if you're more geometric minded, and it's in particular if interested in W algebras or the relation between vertex algebras as such to physics and geometry. That's a good resource, a good modern resource. And the book, the lecture notes by E.G. Huang. He's also writing a book based on these lecture notes. You find at his homepage. That's the one if you are interested in the technicalities, especially the tensor category. Yeah, if you want to have some additional reference to what I'm providing, it's actually the two resources that I consulted for preparation, and it's bits and pieces. Not everything I'm prepared is in there, by far not, at least some pieces. And yeah, okay. I just when I'm home I want to write an email to Jürgen, and he will, or to Jane, and she will forward it to everybody. So it's you find a lot of information on his homepage. Anyway, I promise to send the link. Okay. Good. Let's see. Where did we end up last lecture? Last lecture, I introduced by LKG the simple quotient, the unique simple quotient of the universal affine vertex algebra of G at level K. And I told you that this is interesting if this K is a rational number that is not too negative. I mean, you introduce it for every K, it's just that the two coincide otherwise. And similarly, you can, just to introduce some notation, I can denote by LK rho the simple quotient of the Verma module that I have constructed before. Right? What did I do is I took a finite, not a finite dimension, I took a representation of the Lie superalgebra G. I asked that the central element acts by the scalar k. I then let all positive modes act as 0 on this and the negative one freely. This gives me the Verma module corresponding to the representation rho of G. And that might be simple or not. If it's not, I can take its simple quotient and I denote it by this. Now, you...
There was one word that I didn't hear properly. Did you say you started with a finite dimensional representation or not?
I start with any representation, okay. and that's of course important. Now, a general a question you would like to ask. So now we can finally say a question that you want to ask. You want to and the question is maybe very sloppily stated. What can we say? We say about modules of the simple vertex algebra. So and to give some pointers, what would you more precisely ask? Can you, for example, classify? I started too small again, right? Can you classify simple modules? Can you understand extensions between modules? And most interesting is there a tensor category structure that is somehow interesting? Do you have a notion of tensor product that makes sense? And then if you can do all these 3 points, you of course want to understand more about the tensor category structure. So let me tell you what is known. So if G is a Lie algebra, and if the bilinear form is normalized as in last lecture, this means the norm squared of a long root is 2, then
The algebras, you could be simple, the algebra?
a simple, yes. Then LKG for k a non-negative integer has only finitely many inequivalent simple modules all of them coming from a finite dimensional representation of the horizontal subalgebra, and in fact the category is the category of modules is what is called a modular tensor category. So this means if, and this is called the Wess-Zumino-Witten case, after Wess-Zumino and Witten. It has been known for a long time, though completely proven it has only been in 2005, I think, by E.G. Wang. Anyway, so these are super nice, and this is where the old physics intuition is coming from. And no one can ask what happens if k is not a positive integer. And
Excuse me.
yes?
So, could you repeat finitely many?
Inequivalent simple modules. There's only a finite set of equivalence classes of simple modules. Every
So you
simple
mean equivalent, isomorphic, right?
isomorphic, yeah.
Yeah, okay.
Is there any statement about extensions?
Hmm?
Is there any statement about extensions? Just semi-simple, or
It's a modular tensor, right? And a modular tensor category is a finite, so finitely many inequivalent simples, a semi-simple category that has a braiding, a ribbon structure, and it's non-degenerate. So many words that I will say more about categories later. The point is, positive integer is extremely nice and very well known. And otherwise, I just write almost nothing is known, and I'll see. I will try to. Let's see how the lectures go. How much I will be able to explain to you, because we have made significant progress if we take G to be SL2 here. Okay. Yes.
So I guess this VK, seems functorial enough. If you have maps from the algebras, you probably get maps between these VKs. But what?
Can you say it again?
I imagine that this functor VK, which takes Lie algebra
To vertex algebra?
vertex algebra, that seems like some kind of functor.
Yes.
Okay, but what about LK?
Hmm?
It's less obvious to me that that's some kind
Yes.
of
Yes. You have a functor, but I don't want to explain that here, because that's That's a lot to explain that functor. I can explain it to you in private, okay? It's, would take me more than a lecture to explain that. Yeah. So, any other questions? Okay, so now, otherwise almost nothing is known, but it is known that semi-simplicity will not hold. So you will have modules that are indecomposable but reducible. And in fact, and the problem is there will be some technology to classify simple modules, namely exactly the functor that you want to have. But beyond that functor, there's no, one has to develop technology to get the other results, which one has to work on. Anyway, let me give you an example of the non-semis. Let me give you, maybe first I'll give you two more examples of modules. The one example is the one I introduced last lecture shortly. It's just called pi usually, the Heisenberg vertex algebra, which is just the affine vertex algebra associated to the trivial Lie algebra C, just one-dimensional commutative, right, with the pairing just multiplication. The Heisenberg algebra. And what does C have for simple modules? We know all its simple modules. I mean, these are just one-dimensional modules where the generator acts by multiplication with your favorite scalar, right? So this means a simple module we would just denote by C lambda, one-dimensional module where you fix your generator, 1 for example, and you let it act by multiplication with lambda. And then the Fock module is the corresponding induced module, and it's called the Fock module at weight or off weight lambda. So let me be more specific. The corresponding Lie algebra is the Lie algebra that has bases xn, n, and z, together with one central element, and commutation relations. The commutator of x and n and m is a 0 unless n plus m is equal to 0. That's all. And then this Fock module is generated by a highest weight vector, which is usually denoted by this symbol, on which the horizontal subalgebra acts by or the generator of it acts by multiplication with the scalar lambda. The induced module procedure is that all positive modes act as 0, and then all negative 1 act freely as before. I will not write that down. But one sees here, for the Heisenberg vertex algebra, I get for each complex number, for each possible weight lambda, I get a module, a Fock module, and these are all. So
this bracket lambda is the vector in C lambda, is that right?
yeah, so absolutely, it's the that's right, exactly. Okay. Now, last lecture I told you to a vector superspace you can associate a free field algebra. If it's an even vector space, you get a Heisenberg algebra or a free boson vertex algebra. So C, that's an example of an even vector space. And if we take an odd one, we need a supersymmetric. It means we need an antisymmetric bilinear form on it, so it needs to be even dimensional. So the first odd example would be symplectic fermions. So this, let me just call them SF for symplectic fermions. This would be the affine vertex algebra associated to the supervector space of dimension 2 and purely odd.
Before you go on to some, in this case, what is the statement there? Is this now a simple module?
Yeah, that's a simple p lambda. Right. I wanted to write this in exercise. This is that's a really good exercise. It's maybe not too long. Pi lambda is simple.
For every lambda?
For every lambda, yeah. Independent of lambda.
So it does not depend on k or anything?
No, the k in fact is fixed to be 1 here. Right. If you would if you would introduce a k, then if you take k to be 0, you would get a commutative vertex algebra, which wouldn't be interesting, and as long as it's non-zero, the statement here holds. Okay.
Excuse me.
Yes.
So actually, how do you define this pi lambda? I know how we define c lambda. It is easy, but how do you define pi lambda?
Exactly. So whenever I have the same thing as before, C is a Lie algebra. So I take a module of the Lie algebra, for example, the one-dimensional module where the generator of this one-dimensional Lie algebra acts by multiplication of lambda. So to be more precise, my Lie algebra is the one-dimensional Lie algebra generated by this element x0, right? And it acts. Okay. And then I can always, this is the affinization of this one-dimensional Lie algebra. And the induced module is what this Fock module is. And induced is exactly what I meant here. That means you start with this one-dimensional module, you promote it. So it's the construction we have seen quite a few times now. Right?
Thank you.
You're welcome. Okay, now I continue with a commutative algebra, but now I make it a commutative superalgebra. This means I take a 0/2-dimensional superspace. That means 2-dimensional vector space, but purely odd. All right, so we can. So you should think about. What? Let me write down as a gen.
Use another pen.
It's already. This is all. Sure. So we can be explicit. This is so it's 2-dimensional vector space. I introduce basis vectors, which I like to denote by chi plus and chi minus. And it's a commutative superalgebra. This means the only relation you require is that they supercommute. And which means if I change the order, I get a minus sign. That's all. Okay, and that's a Lie superalgebra, so I can take its affinization, and it has the name symplectic fermions. It's the name that physicists introduced to this. Now I can do. So now one can also try to classify simple modules. And how many simple modules do you think this algebra has? Any guess? Yes?
1.
That's a very good guess. That's correct. So. Okay. So how did you come up with this guess?
The answer is always 0.
I should not have asked that. We can think about it. What are possible modules of this this algebra? But I mean, this these are odd, so we also require the relations that they square to 0. And so they are nilpotent operators, right? I mean, it doesn't really make sense to come up here with weight modules. There's simply no room to find a weight label also that introduces a family of modules. Anyway, so does this mean that every module is a direct sum of these simple modules? What do you think?
Excuse me, what do you mean by they square to 0? It's just a linear algebra.
Right, that is now in the universal enveloping algebra.
But then why do they square to 0?
Because they are odd. So the universal enveloping algebra of the symplectic fermion is polynomials, and these two variables is subject to these three relations. It's just the exterior algebra in two variables.
That's new information, or that's supposed to follow from
It's not new information, because this is a commute. So we are working over the complex number. So the commutator of chi plus with itself is just 2 times chi plus. The one of 2 times chi minus with itself is 2 times chi minus. So these three statements are just saying that this is a commutative superalgebra. So it's not new information.
Okay, thank you.
Yeah. Okay, good. But yeah, good question. So anyhow, can you come up with a module that is not a direct sum of? And now we are only talking about this Lie, this finite dimensional Lie superalgebra. Can you come up with a module of this finite dimensional Lie superalgebra that is not a direct sum of trivial modules? So. Bless you. Think about it. We have one obvious module. So I mean, we have the trivial module as one obvious module. We have another obvious one, namely the universal enveloping algebra itself. Right? The universal enveloping algebra is just polynomials and chi plus and chi minus subject to these three relations. So this means so if you look at the universal enveloping algebra of this Lie superalgebra, that's just a 4-dimensional algebra spanned, of course, by the constant polynomials, by chi plus, chi minus, and chi plus, chi minus. I don't have anything else because each of these squares to 0, and chi minus times chi plus is just this up to a sign. So it's just a 4-dimensional module, right? And how does this is a 4-dimensional module generated by a single vector 1, right? Because how do I get from this basis vector to this one? I multiply by chi plus. How do I get from this one to this one? I multiply by chi minus. And then I multiply by the missing one, and I go to this one. And clearly, I have no element in this Lie superalgebra that maps chi plus to 1. Right? Clearly, I have no one here or here, so the action only goes down here. Right? So we get we get a very nice 4-dimensional indecomposable module for this commutative Lie superalgebra, this supercommutative algebra. Okay. And now we can remember this induced module construction works for any module of the horizontal subalgebra. So in particular, it works for this one. And now let's just give it a name. I call it P to be the induced module of this one. Right? And this indecomposability structure persists. So that means what you get is that this module P, I write dots here has the following structure. It is a small diamond. So this is called a small diamond. And it has this structure. And this thing here is called a Löwy diagram. It means P is a module of the symplectic fermion algebra that has 4 composition factors, each of them of the same type. It has a simple submodule, which is this one. If I quotient by this one, the quotient has the direct sum of these two as semi-simple submodule. If you quotient by that one, you get this one. The arrows mean that you have a non-trivial extension between these two modules, these two.
Yeah, this was too much information.
And I will write everything I said down now. Right? I just wanted to say it in words first in this example. And now I go to this side of the board so what you see here is that while that in the superalgebra setting we very, very quickly already come to kind of interesting indecomposable modules. So the non-semi-simplicity appears quite quickly. This is not a surprise, because what do we know about finite dimensional simple Lie algebras? We know that finite dimensional modules on which the Cartan subalgebra acts semi-simply are always direct sums of simple modules. What do we know about finite dimensional modules of finite dimensional simple Lie superalgebras? We know that this statement is not correct except for OSB 1/2n. So except for a very special series, Lie superalgebras always have already finite dimensional non-semi-simple modules on which the Cartan subalgebra acts semi-simple. So somehow this indecomposability is much more naturally encoded in Lie superalgebra. Okay, so let this module P here has the property P is both projective and injective. And I just erased here, but what I wrote here is if we have a vertex algebra and modules, we want to understand what are its simple modules, classify them, and then we want to understand indecomposable modules. And understand is again sloppy. So one thing what I like to mean under this, I would like to classify all projective and injective modules, and I would like to be able to write down their Löwy diagrams, because the Löwy diagrams are an extremely convenient way to encode the complete extension structure in a single diagram. So let me tell you what all these words mean, so that we have these categorical basics. So what does it mean for a module to be projective? It means if I have a short exact sequence where the P is the quotient, then this needs to split no matter what you take for A and B. Splits always. So projective modules don't allow for non-trivial extensions. Similarly, injective, you just have to put it's injective if it can't appear as a proper submodule of a non-trivial extension. So any short exact sequence of this type always splits as well. Right. So this means modules that are projective are, modules that are both projective and injective are largest possible extensions in this sense. All right? And it's clear that if you have if you understand all modules that are projective or injective, ideally both of them, you understood a lot. It turns out, for some miracle that is not understood, in all VOA categories that we do understand, projectives are injective and vice versa. So this is sometimes called unimodularity, and there should be a reason for that. It's not clear what it is. Any questions? Okay. Now we come to the Löwy diagram. So and some more so if you do the exercise and try to write all possible extensions that are involved in this P, then I mean all extensions that you need in order to completely characterize P, it wouldn't be long, but it would still be quite a bit to write. The Löwy diagram is definitely the most convenient way to encode the information. So what do? We start with M, a module in our category, and then we say the circle of M is the maximal completely reducible submodule of M. Right, so in that case, it would be a single copy of the symplectic fermions. It is so then next the Sokal series is the sequence so this is a Sokal series of length L, where the quotient mi modulo mi minus 1 is the Sokal of our big module quotient by the. So here we have a sequence of submodules. We can we can quotient by them. And yeah, so if you look at this picture, for example, we can quotient by its Sokal, its simple submodule. That would the quotient would be a module that would have this Löwy diagram, meaning it would be a module that has two copies of this one as submodules. So that means the Sokal of the quotient is the direct sum of these two, and that would be then our M1. And then our M2 would be the next quotient, so that and that would be just this SF. So this means the Löwy the layers of the Löwy diagram, they give us the successive Sokals in the Sokal series. Okay, good. So and with this notation, now we come to the Löwy diagram. So we have a module that has a Sokal series of length L, and then the Löwy diagram of M has L layers, so as many as length of the series. And the ith layer consists of the direct summons of the corresponding term in the Sokal series.
I'm confused how P can be projective and injective, and yet have this SF sitting inside in a non-split-off way. And clearly there's a map from SF to P, and then you're claiming it's not split, right? But you just told us that split means.
So yeah, there's
I see. Never mind. I just confused myself.
okay, that's good. It's in fact quite a common thing to be both. So anyway, we have this filtration of submodules with this property. So this means each such a quotient is semi-simple. So we can write it down as a sum of potentially a bunch of simple modules. And then the ith layer of the diagram is just you write down I dots, and each dot you label by one, not I, ni dots, and each dot you label by one of those modules. And then we also have arrows. So when do you, let me draw the picture. So this means we have here at the top the simple summons of the top module. And then we have a second layer, and we have then N2, and then we write down the N2 direct summons that appear in the second layer, and so on up to the original Sokal. And now, in addition, I also wrote arrows. So where do we write arrows? And then we write an arrow from one Löwy layer to one layer down, only one layer down. From CIA to CI I minus 1b if the quotient mi modulo mi minus 2, so that's the quotient whose Sokal is exactly, so where the ci minus 1b is a summand of the Sokal. If this one has a submodule E that satisfies that the circle of E is this CBI minus 1, and the quotient of this one is the module that appears one layer higher. If there exists a submodule E satisfying this one, and of course non-split. Otherwise, I would have to draw an arrow from everything to everything. Okay, this is very long to explain what a Löwy diagram is. I wrote it down quite explicitly. And now I write this down because I mean, writing down all possible extensions, you can do that, and this is of course also instructive, but it's very hard to keep it in mind and also go on just because it's so convoluted. The Löwy diagram is always nice, right? I mean, it's just a small diagram, and you can read off a lot from it. So let me explain it again in this diagram, what it means. We have here a module that is indecomposable, so this means it's it has a single simple submodule, and that's what you see at the bottom of the diagram. So it has this as a submodule. This submodule allows for extensions. It can be extended by this module and by this module. So really, the x1 of this module by itself is two-dimensional, is what this is saying. Right? So the arrows, these arrows says there exists an extension, an indecomposable module that has this one as a submodule and this one as a quotient.
Why that diagram is saying that some of x is two-dimensional. It certainly says self x not 0. I understand that.
Yes. Right. You mean why aren't these extensions the same?
Yeah, could be.
Right. Right. I take it back, but in this case, the extension is indeed two-dimensional, and I'll tell you in a minute how to read it off from this. But yeah, no. So all this diagram is saying it has this projective. This module has this one as submodule. There exists an extension that has this one as submodule and this one as quotient. This one as submodule and this one as a quotient. These two can be combined to an extension that has this one as submodule and the direct sum of these two as a quotient, and that can be then further extended to a module that has this Löwy diagram. And it's already getting harder and harder to say in words what it is. Right. And now I'm sorry, in order to read off the extensions you read off by writing down projective resolutions and then taking homology of that. Which we can maybe do later. Any questions to this?
Yes.
Yeah.
What's the dimension of SF?
It's well, SF is the vertex algebra itself. It's infinite dimensional. Right? It's the vertex algebra now. Here I did it for the horizontal subalgebra. Here every component was one-dimensional. These are modules of the horizontal subalgebra. This commutative Lie algebra, which is now erased. Each module induces to a module of the affine vertex algebra. And that the corresponding module I called P. It has the same type of Löwy diagram, but of course now every composition factor is a module of the affine vertex algebra, in particular infinite dimensional.
And what is there as a correspondence between this Löwy diagram and this Löwy diagram?
Well, even the categories are equivalent as abelian categories.
Yes,
So
I can see that, but I mean, why? I mean, is like P really just? I mean, is there some way to say the SF at the top of P is usually SF times 1, and the SF
Yeah.
SF plus and
yeah,
in some sense?
So why don't we make a break, and whoever stays, I will answer the questions. So we have, these modules are labeled, graded by conformal weight, right? We have which in this case they are labeled by.
I think you're making it very hard for anyone to take a break.
Okay, then I will continue after the break with this question.